Hey everyone, so welcome to the third lesson of Unit 1 for Calculus. Today we're going to talk about the concept of a limit not existing. The limit does not exist. And if you remember, the idea of a limit was that as you moved towards a specific x value from the left, and as you move to a specific x value from the right, as those approach that x value, if they are approaching a specific y value, then you have a limit. The limit exists. The idea of a limit not existing, and there's a few different scenarios where you'll see this, but when your left-hand limit, so as you get closer and closer and closer to an x value, let's say this is approaching the y value of 3, and then from the right-hand side, this part of the function is approaching, when x equals whatever, is approaching 4, since the y values are different, we would say the limit does not exist. So with that said, let's go ahead and get into it. And that's exactly what the objective talks about. I can determine if a limit exists based on its right hand and left hand limits. First of all, let's go back a little bit and talk about the analytical approach to determining limits. Remember, I showed you how to determine a limit by substitution. And if you can plug in a number and basically get an answer out, essentially, if the function's continuous at this point, then I can just substitute, okay? If that's not the case, then we try other things like factoring or multiplying by conjugates or something along those lines. But the bottom line is, throughout all of that, all you're doing is algebraically manipulating the function so that it looks different than what it is, than what you started with, so that maybe you can eliminate something or you can see it in a different way, so you can therefore determine the limit. So let's go ahead and take a look at this example here. We have the limit as x approaches 0, limit as x approaches 0 of sine of x over 2x squared minus x. Now, this looks really complicated with where we're at right now. I mean, 3 days into calculus. But if I can manipulate that algebraically somehow, I can determine the limit. And so here's the idea. I know, and I told you to memorize this, I believe, after lesson 1, I know that the limit as x approaches 0 of sine of x over x is 1. That is something that we discovered through numerical methods looking at tables, and I said I would prove it to you later on, and I will later on. But we can use this idea if I can manipulate this algebraically somehow. So remember, if I go to substitute, let's go ahead and try substitution. So that would be sine of 0 over 2 times 0 squared minus 0. Well, sine of 0 is 0, and then that on the bottom is 0. So what do we call that? That was indeterminate. Indeterminate. I guess I should have kind of done that before I talked about this, but I knew where I was going with this. So now I can rewrite this, and remember the next step is maybe to try to factor. And in fact, factoring will work here. It's going to be a little bit different of a look than the kind of factoring that we did before. But let's rewrite this with a factor involved. That'd be sine of x over x times 2x minus 1. You see, by factoring, we start seeing this function that we talked about in prior lessons. So I can now rewrite this as the limit as x approaches 0 of sine of x over x times 1 over 2x minus 1. Now, some of you might be going, well, wait a minute. How do you know that you're gonna do that? Like, what's the indicator? And a lot of it is just feeling comfortable with the mathematics and seeing something going on, seeing a relationship, and maybe just trying to make it look like you have this, okay? Now, we have a rule in calculus that basically says the limit of a function, of like a product, is going to be the product of the limits. So again, if you can just manipulate it algebraically. So this actually is the same as the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over 2x minus 1. And so now we have two separate limits, and we already know the answer to this guy. This guy right here was 1, okay? And then we're going to try substitution here, so we end up with 1 over 2 times 0 minus 1. So this becomes 1 times 2 times 0 is 0, minus 1 is negative 1, so 1 over negative 1 is negative 1. And so our answer is negative 1. The point being is that you can manipulate the functions so that they appear to be different or look different, and then separate them somehow so you can see that, okay? So we factored here, and then we rewrote it as a product of two separate functions. Since I knew the limit of this guy as x approaches 0, I can just replace that with that value. And then I can figure out this limit by just substituting 0 in, okay? So, and you can see that, try manipulating algebraically. We know the limit as x approaches 0 of both of these functions, and so the end result is negative 1, okay? All right. So, and this is kind of the crux of the whole point. If a function is any combination of other functions, multiplication, addition, subtraction, division, or whatever it is, then the limit of the function is equal to the combination of those limits. The combination of these limits is the same as the limit of the original function. You just have to be careful that you're not dividing by 0. You can't say, you know, the limit of the top divided by the limit of the bottom, and the bottom is 0. You're going to have a problem there. Okay, so here's an example that I want you to think your way through and see if you can come up with it. Pause the video, and then when you think you have an answer, come back and see how you did. Okay, so in this problem we have the limit as x approaches 0 of tangent of x over x. Now, that looks totally different. In one regard, it's a tangent. But see, now we're starting to recognize something's going on here. I know that there's, the only limit I really know, the only thing I really know right now is one trig function, and that is sine of x over x when it's the limit as x approaches 0. Well, we have the limit as x approaches 0, so that's good. And we have some trig function over x, so that's good. We just have to figure out how we can rewrite that so that we have a sine x somewhere in here. And if you remember, this is going to be dealing with trig identities. We know that the tangent of x, let me write this down over here, the tangent of x is equal to sine of x over cosine of x, right? Sine over cosine. Now again, I guess I'm jumping the gun because remember I told you the other day, you have to make sure you're substituting before you do anything else. So if I plug in 0, tangent of 0 is 0 over 0, so we have indeterminate form. You need to show that work too. But anyway, since tangent of x is equal to sine x over cosine of x, I can rewrite this as the limit as x approaches 0 of sine of x over x times cosine of x. Hopefully you agree with me on there. That's just algebra at its best. Sine over cosine is tangent, and it reworks like that. Well, there's my sine of x over x, so then I can rewrite this as the limit as x approaches 0 of sine of x over x times 1 over cosine of x. So we're taking the limit of this product, and now we can say the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over cosine of x. And then we know that this guy right here is 1, so we can replace that. And then this one, well, we're going to just substitute and see what we get. 1 over cosine of 0. And cosine of 0 is 1. So 1 over 1. And so 1 times 1 is 1. Okay? What you're going to need to have in your repertoire of mathematics is a decent understanding of those trig identities. Not that we're going to go too deep into the double angle formula and the half angle formula and all that, but it's going to be very good that you remember that tangent is sine over cosine. Remember, sine squared plus cosine squared is 1. Things like your inverse trig, not your inverse, your reciprocal trig, like secant is 1 over cosine, cosecant is 1 over sine, cotangent is 1 over tangent, and cotangent is also cosine over sine. Those kind of things you should recall pretty easily, hopefully. I know it might take some brain power there. So like I said, just manipulate it so it gets to the point where it looks like something familiar to you. And again, we should be substituting first, but we end up with 1 there. All right, with that said, let's go ahead and take a look at the idea of a one-sided limit. One-sided limit. What we were talking about before with the definition of a limit is the idea that the limit from one side is the same as the limit from the other. But now we're going to only focus on one side. So let's say I'm looking for a limit as x approaches 5, but I only care about what's happening from the left-hand side. Okay? So one-sided limits. A left-hand limit is the value that the function approaches as x gets closer and closer to a specific c value from the left side. And then the right-hand limit would be exactly the opposite of that. It's written as the limit as x approaches c from the left of f of x. I'm going to write this down so that I can emphasize it. The limit as x approaches c. Now normally that's what we're saying. That's what we've been saying all along. But we're going to put this little negative sign there to represent that we're only focusing on the limit from the left-hand side. So of f of x. Okay, so we are looking at only the left-hand limit. And then of course the right-hand limit is the limit as x approaches c from the positive side of f of x. Okay, so that tells you, that little plus and minus sign tells you that you're talking about the left or the right hand only. And again, the right hand limit is the value that f of x approaches as x gets closer to a specific c value from the right hand side. And that c value, notice, is an x value basically. Okay, and it's written as the limit as x approaches c from the right of f of x. Let's go ahead and take a look at a graph of what that looks like. It says, so we have this graph, and you can see a lot of things going on. We got a piecewise function, and it would take us a little while to write that piecewise function. But let's take a look at what it's saying. It's saying, what is the limit as x approaches 1 from the left, sorry, negative 1 from the left of f of x. So looking at the lesson here, let's take a look. We're looking at negative 1, x equals negative 1, and we're trying to approach the x value from the left-hand side. So if I move my cursor from the left to the right, what do we see? What do we see the function approaching from the right-hand side? Well, we see that it's getting closer and closer to this value. The function is not 3 there. We're not saying that f of negative 1 is 3. We're saying the limit as x approaches negative 1 is 3. Okay? What is it getting closer and closer and closer to? What's it inching towards? Not what is it actually touching. Okay? Remember that open circle means does not exist there. And then the limit as, let's do the other one, the limit as x approaches negative 1 from the right of f of x. Well, if I'm looking at it from the right, so I'm moving from right to left and I'm getting closer and closer to this x value, what is that approaching? Well, that's approaching a y value of negative 2. Now, again, it does not matter that the function exists at a certain point or not. What matters is what is the function getting closer and closer and closer to. I think I might have said this the other day, but if I'm walking towards the wall here and I never actually touch the wall, but like let's say I'm taking a step and I count the distance from here to the wall and I walk halfway and then I walk another halfway and then another halfway, and then another halfway. Am I ever actually going to touch the wall? No, because I'm only cutting my distances in half. But I am getting closer and closer and closer to that wall, in that very specific place. Okay? Let's go ahead and take a look at the next question. What is the limit as x approaches negative 1 of f of x? So this is just saying what's the limit overall. Here's where a lot of students fall into a trap. They say, well, look, there's a closed circle here. So since f of negative 1 is negative 2, and that's true because there's a closed circle, then the limit must also be negative 2. That's not true. That's not true. Because technically, this can only exist, the limit as x approaches negative 1 can only exist if the left-hand limit and the right-hand limit produce the same values. Since the left-hand limit produces 3 and the right-hand limit produces -2, we would say that this limit does not exist. Okay? So I hope that kind of makes sense as I go through this. Let's go ahead and take a look at another example of this. Okay? And this is important to write down. A limit at a specific point can only exist if the left-hand and right-hand limits both exist and are the same. So we're going to get into these limits not existing at all, but and specifically when you're talking about asymptotes, but we'll get more into that in the future. These have to exist, and they do because they're numeric values, but they have to be the same in order for this one to exist. Okay? Notice the notation that I'm using here. Year over year over year, students constantly use wrong notation. This says the limit as x approaches -1 from the left of f of x. Okay? So in a sense, this is the noun, f of x is the noun, and this is the action on the noun. This is the verb. This is what we're trying to accomplish, determining the limit of this object. If you just write the limit as x approaches -1, you have a verb, but you don't have a subject for that verb. So this doesn't make any sense, and I see this all the time in here. And so the justification for this guy, it does not exist since the limit as x approaches -1 from the left does not equal the limit as x approaches -1 from the right. This is what I see all the time for justification. This is not acceptable because the verb cannot equal a verb. You have to have a subject for your verb. So you've got to have that f of x or g of x or whatever the function's name is in there. So the limit as x approaches -1 from the left of f of x is not equal to the limit as x approaches -1 from the right of f of x. So the limit does not exist because the left and right hand limits are not the same. All right. Go ahead and give this one a shot and see what you come up with. What is the limit as x approaches 3 from the left of f of x? From the right, as x approaches 3 from the right of f of x, what's the limit as x approaches 3 of f of x, and what is f of 3? So, limit as x approaches 3 from the left of f of x, limit as x approaches 3 from the right of f of x, the limit as x approaches 3 of f of x, and then f of 3. These are all 4 different questions. Well, what is the left-hand limit? So if I'm looking at approaching 3 from the left-hand side, what is the y value getting closer and closer and closer to? It's getting closer and closer and closer to this value of 1. Okay? It's not getting closer to 2. Just because that's a closed dot doesn't mean that's a limit. What is, I'm tracing the function. What is it getting closer to, right? If you have to pick up your pencil and put it somewhere else, then that is not going to be the right answer, okay? The limit as x approaches 3 from the right, what is it getting closer and closer to? We see that it's getting closer and closer to 1. Since the two limits, the left and right hand limit, whoops, I got this wrong, sorry. Those are both 1s. Okay? Since the left and right hand limit are the same and they exist, we can say that the limit as x approaches 3 of f of x does equal 1 because they're the same. Now, what's f of 3? F of 3 is the actual y value of the function when x equals 3. And if you look at this graph, if I go over 3, what is the function's value? It is that dot. And so we can say f of 3 is 2. So you can see that the limit might be one value, but the function at that point might be a different value. We're going to get more into this later on, but this means the function's not continuous at that point, and you can see that it's not continuous at that point based on what you've known from the past. All right, so 1, 1, 1, and 2. Let's go ahead and do another one. The limit as x approaches -6 from the right, -6, and f of -6. So I'm not clearly defining some of this stuff. A lot of it is just a matter of seeing an example of it so you can see what's going on. Okay, limit as x approaches -6 and f of -6. All right, the limit as x approaches -6 from the right. So if I'm going to trace this from the right, what am I getting closer and closer to? From the right, I'm getting closer and closer to 2. What is the limit as x approaches negative 6 of f of x? Well, the right-hand limit is 2. There is no left-hand limit. There is no left-hand limit. So we would say does not exist. Okay? Why is that? Since the limit as x approaches negative 6 from the left of f of x does not exist. See that? And then you can go further, and since that doesn't exist, there's no way that it can match that, right? So or therefore, the limit as x approaches negative 6 from the left of f of x cannot equal the limit as x approaches negative 6 from the right of f of x. So you can see that the limit does not exist because the left-hand limit does not exist, which implies that the left-hand limit can't equal the right-hand limit, okay? But we don't have to write this statement down. We would be good with writing that statement down. And then f of negative 6, what is the function's value at negative 6? Well, we would say that is 2. All right. Let's go ahead and take a look at another example. It says graph the function and identify the left-hand limit, right-hand limit, and limits, if they exist, at x equals 0, x equals 1, 2, 3, and 4. It looks like we got a lot of stuff going on here. Well, I'm going to go ahead and graph it just because it's good practice when it comes to piecewise functions. We have negative x plus 1, which means we're going to go up 1 and have a negative slope. So we have something like this. And we have an interval from 0 to 1. So really, it's only 0 to 1. That's 1. And it's a closed interval here and an open interval there, so it doesn't count. And then we have 1, the constant 1 from 1 to 2. So it's that. And it's going to be closed here and open there. We have 2 2 at 2. So that's 2. And then we have, from 2 to 3, we have a line with a y-intercept of negative 1 and a slope of 1. So that's kind of nice that kind of just passes through all that pretty easily. Okay, so because I went up 1 over 1, up 1 over 1, it worked out. And then from 3 to 4, we have negative x plus 5. So 3, 4, 5, then down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1 to 4. Okay, so that's what the piecewise function should look like when you're all said and done. And we are looking for the limit of each, the left and right-hand limit at each one of these. So the limit as x approaches 0 from the left, the limit as x approaches 0 from the right, the limit as x approaches 0, okay, and left-hand limit, right-hand limit, and limits. Okay, just limits. So I'm going to just write all these out. The limit as x approaches 1 from the left of f of x, the limit as x approaches 1 from the right of f of x, the limit as x approaches 1 of f of x. So we'll do these 3 or these 6 here, and then I'll put it on the Dessert thing. So what is happening as x approaches 0 from the left? Well, there's nothing going on to the left of that. So this one is a does not exist. Okay. The limit as x approaches 0 from the right, so from right to left, what is it getting closer to? It's getting closer to 1. What's the limit as x approaches 0 overall? Well, remember, for that to happen, the two limits from the left and right have to be the same. Since that one does not exist, that one does not exist. And we would say since the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right. Okay. Now the limit as x approaches 1 from the left is 0. The limit as x approaches 1 from the right is 1. And since these don't match, this also does not exist. I should actually, the justification on this one is inaccurate. I mean, it's not complete. We should say since that one does not exist. This justification would be since this does not equal that. Okay, so that's from 0 and 1. Now let's look at 2. The The limit as x approaches 2 from the left is 1. The limit as x approaches 2 from the right is 1. And therefore, the limit as x approaches 2 is 1. Okay, so I'm going to go ahead and write some of this out so we can have it. Okay. So 2 is 1, 1, and 1. But what is f of 2? F of 2 is 2. But it doesn't matter what the function's value is when we're talking about limits. We're looking at what it's approaching. All right, for the limit as x approaches 3 from the left we're approaching 2. From the right we're approaching 2. And since those two limits are the same, that means the limit exists and it is 2. Okay? It so happens that f of 3 is also 2, which means it's continuous at that point. And that's actually the definition of continuity at a point. The limit as x approaches 4 from the left is 1. The limit as x approaches 4 from the right does not exist because there's nothing over here. And therefore, the limit as x approaches 4 overall does not exist. Okay? And so, okay, what's going on here? There we go. All right, so there's that. The next slide. Got an exit problem here. And we are given a piecewise function. Oh no! Piecewise function. Especially with that one. Let's see here. We have something pretty gross. Let's see. We've got f of x equals piecewise radical 1 minus x squared from 0 to 1. We have 1 from 1 to 2, and we have 2 from x equals 2. Okay, so it says draw the graph of the function, and what points in the domain does the limit not exist? Well, graphically, we can see it a lot easier. What in the world is that function? Some of you should recognize this because I know I've taught it to you. This is a semicircle because it's got an x squared inside the radical, and we're taking a constant and subtracting the x squared. It's got a radius of 1 because the square root of 1 is 1, and it's the top half of the circle because it's positive, not negative. So this has a radius of 1, centered at 0, 0, because there's no shift there, and it's the top half of the circle. Now we are looking at the interval from 0 to 1, so we're looking at only this piece right here, okay? And this is a closed circle, and this is an open circle, okay? Now, from 1 to 2, we have a constant of 1. This is closed, and this is open. And then at 2, we have a value of 2 right there. So that's the graph of the function. And the question is, at what points in the domain does the limit not exist? Well, looking at it from left to right, is x equals 0 in the domain? Yeah, it is. So does the limit exist there? So we would say limit of f of x as x approaches 0 does not exist. Why? Because the left-hand limit doesn't exist. Since limit as x approaches 0 from the left of f of x does not exist. Okay? Now, moving along here, that's continuous, continuous, nice, clean, continuous. Uh-oh, we have what's called a jump, and we'll get more into that in the future. The limit as x approaches 1 of f of x does not exist. And the reason there is because the left-hand limit is 0, the right-hand limit is 1. So since the limit as x approaches 1 from the left is not the same as the limit as x approaches 1 from the right of f of x. Okay? And then over here, we would say the limit as x approaches 2 of f of x does not exist, since for basically the same reason as up here. The limit as x approaches 2 from the right of f of x does not exist. Okay? So those are all our points of discontinuity. In other words, that is a place where the limits do not exist. All right, that wraps up. Let's see if I got that right here. Okay, looks good. That wraps up this lesson. Hopefully you have a good understanding of what it means for a limit not to exist, at least from a graphical standpoint. If you have any questions, please reach out to me. Otherwise, I will talk to you later.